Here we have a matrix. The matrix has a kernel. But what is the dimension of the image? It is a very interesting exercise and a thought-provoking one. I like it because it links many different things together. It really focuses on the conceptual understanding of a matrix, which we keep reiterating here in the tutorials, and that is the matrix is just a linear map. The matrix is a linear map from a vector space V to a vector space W. This is not relevant. What is relevant here is the dimension of vector space W and the dimension of the vector space, V and the dimension of vector space W. I said W and I was talking about V. This is fine. Well, we know that A is n times k, so I'll tell you this. If A is n times k, then A takes an n-dimensional vector and it returns a k-dimensional vector. This is for sure. I tell you this for sure. So the dimension of the input, you could say, is n, but at the same time it outputs a vector of length k, which is the length of the vectors in the new vector space, so to say. So this is good. We know that the dimension of the image of the map will involve k in some capacity. Why is it not simply going to be k? Well, because some maps do not have a full rank. By this, I mean some maps do not preserve the data, you could say. Some maps lose their data. Precisely, this is done when you send your elements to 0. For example, is a very, 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 very simple example. We take f of x is equal to 0. This is a map which has absolutely no data, because if I give you x, you can give me 0. But if I give you 0, can you tell me which x got sent to 0? No, you can't tell me, because every single element in the vector space gets sent to 0. This is a very extreme example, but you could imagine that this matrix, as a linear map, has some set of vectors which get sent to 0. Perhaps this will be a bit more clear if we refresh on what the definition of a kernel is. This is the definition. The kernel of A is all the vectors x that give us 0. Or you could say all the vectors x that get sent to 0. For example, here, the kernel of f is all real numbers. If we assume that f is a map from R to R, for example, this is a very simple example, then this map has the kernel, which is the whole space. But this is a very extreme example. If we have a space which is, let's say, 10-dimensional, we could have a map that preserves the data of 8 dimensions and sends 2 dimensions, for example, to the 0 vector. And you know for sure that these 2 dimensions you cannot retrieve. What do I mean by 2 dimensions? I mean 2 lines. And guess what? This is the kernel here. Here it is the span of these 2 vectors. Let's now understand what this means. The span of 2 vectors is every single vector you could reach by scaling the vectors and adding them. So it is precisely alpha 1, 2, 1, 0 plus alpha 2 minus 2, 1, 0, where alpha 1 and alpha 2 are elements of the field of scalars. I don't know what the field here is. You could think of it as, you know, some constant, but here for the technical correctness of this, I just put a field. A field is a place where you obtain your scalings from. So for all scalings, you look at this. Intuitively, when I say span, I mean that we usually have two vectors, and we look at every single vector we can reach by scaling and adding these two vectors. For example, if I just scale this vector, I would get these vectors. Maybe I'll draw a long line that goes through them. Okay, this line does not go through them. I have a bad intuition of how a line should look like. Oh, maybe it's not so bad, at least in one of the cases. So you could think of all the possible scalings of the vectors, but also do not forget to add them. Now, when we add two vectors, we take the vector and we place it on top of the other vector. So if I do like this in this motion, I take the end of the vector and I sweep it all over the line, and I also have the freedom to extend this as much as I can and retract it as much as I can. Then I can confidently say that any point on this space that you can see right in front of you can be attained by some linear combination of these two vectors, these two lines, really. Now, what does this mean? It means that, you know, the span is two-dimensional. This I can say for sure. You know, you have two vectors in space. They span they span two dimensions. This is, I think, is very clear. Is very intuitive. You have two vectors in space. So here we have the span. We know the span is two-dimensional. So if I write this on the side now, the dimension of the span, which is the dimension of the kernel, you could say, the dimension of the vectors that get sent to 0 is 2. I can say this very confidently. You have one vector, you have the other vector, and these two vectors are linearly independent, by the way. If they are linearly dependent, then they would just span one line. So for example, these are two vectors which are linearly dependent. It's just the same vector, but with a difference in sign. So I think here it is very clear that they are linearly independent. There's no way you could scale one of these two vectors to get the other one, or any way that you would cancel them out together to get the 0 vector. So we know these two vectors span two dimensions. Now, the rank nullity theorem is the keyword here. The rank nullity theorem tells you that your matrix, if it outputs a k-dimensional vector, like in this case, then the dimension of the kernel plus the dimension of the image should give you k. I think this is very intuitive. When I say dimension of the kernel of A plus the dimension of the image of A is equal to k. Why is this the case? Let's go back to the example where we have a 10-dimensional vector space, and we have two dimensions which get sent to the 0 vector, then clearly the other 8 dimensions get sent through the image of the map. The image of the map is all the possible values it can attain when you plug in all the possible inputs. So I can confidently say that since the image, not the image, since the resulting vectors lie in a k-dimensional space, and there are 2 dimensions which go to 0, then the remaining dimensions go, the remaining dimensions are k minus 2, and there are k minus 2 dimensions which go not to 0. This is what I can say for sure. So I hope this is a good explanation of the fact. I'm trying to think of a better way to phrase this. But in short, perhaps I'll say this one more time. If you have a map like the matrix A, and you have 2 dimensions which get sent to the 0 vector, then there are k minus 2 vectors which do not get sent to 0 vector. These dimensions which do not get sent to 0 are the image of the matrix. And naturally, these 2 things should add up, because the map will send some values to 0 and some values somewhere else. It cannot send them to any other place. And this is kind of the proof for the rank nullity theorem. It's not a proof, it's a proof idea, you could say. And from there, you know that the sum should be equal to k. You know that this is equal to 2, then that definitely should be equal to k minus 2. It is not n minus 2, because n is the input vector. It is not the output vector. We focus on the output, which is k-dimensional. 2 of them, of these dimensions, get sent to 0, and the rest, the remaining, are part of the image. These are precisely the dimension of the image. So that is, of course, one way to think about the rank nullity theorem.